you very much. Thank you for the invitation. So the idea of this talk is to do what to realize Karim's grand vision of me being a sort of bridge between different teams. And so the idea is that I'm going to do a talk which will be about categories in some sense, so which will be a bit boring to people who already know very much about categories, and a bit too abstract for people who don't care about categories. And the idea is that no one will be satisfied, but at least everyone will have something. Okay. And yeah, so the thing is that in my own research, one of the main construction that I did is a certain graded ring, certain graded object. And at first I did it naively. I constructed a ring, it has satisfied all the conditions by hand. And then I refined the construction and realized that it was all automatic if we use the right setting and the right understanding about what a graded object should be and how should we prove that it is. So you see that it's in the end very simple. It's just so I just want to convince people that it is a correct point of view and that it makes a lot of constructions seem quite natural. Okay. So a lot of it is going to be me introducing monoidal categories, which are sort of like, as the name suggests, the equivalent for categories as monoids are for sets. Okay? So monoids are sets with a multiplication. Monoidal categories are categories with a multiplication. Okay? With the idea that a set is a 0 category and a category is a 1 category. And so all those constructions can be generalized to higher categories. I'll just bridge on it just to arouse a bit of interest, but that would be it. Okay, so let's start with categories. So remember that in a category, in category theory, there are 3 layers. You have your categories, those are sort of like your basic objects. You have functors, which are like morphisms between categories. But you have a 3rd layer, which is natural transformations, which is morphisms between morphisms. Okay? So I assume that everyone knows what a category is, what a functor, what natural transformation is. And we'll take it from here. Okay? And so this is because when you work inside a category, like if you work with, I don't know, you work with rings, so you work inside a category of ring, you are working inside a 1 category. So you have objects and morphisms. But if you're doing category theory, you are working in the category of categories, and this is a 2 category. So it has 0 morphisms, 1 morphisms, and 2 morphisms, which is why there are 3 layers. And this is kind of the whole point, actually, of category theory. It was introduced because people needed to understand the 3rd layer. Okay. Now we are going to add a product on the category, which make it look like monoid. Okay. So we're going to work with 3 basic examples of categories. Maybe I'll try to color code them if I can remember it. So first example will be a discrete category. So it's kind of sort of like the simplest example of a category, which is a category which is actually just a set. Forget about all the added bells and whistles of category, it's just a set. So you start with a set, and then I will denote, so C, curly C, Pascal C will be my general symbol for category. And for this one, I will note bracket X. Okay. So it's a discrete category on the set X. And so what is it? What is it? Well, the objects are the elements of X. And the morphisms, well, either you only have identities, you only have the identity morphism. So morphism, the set of morphism from two objects is empty if X is not Y, and there's just the identity of X if X is Y. So basically, you have no morphisms. Either two objects are equal or they are not equal. You know, in a category, the correct notion is not equality, it's isomorphism. But in the discrete category, isomorphism is equality. So there is completely rigid. It's just a set. So that's the first example. We'll see. Like, it might seem that okay, but this is then extremely boring. Like, is it really interesting? But we see that it's crucial in what we want to do. A second example will be, let's fix R a commutative ring. And then we'll look at the category of R modules. So I will not broach any size issues in this talk. You can pretend that you have fixed a large cardinal and everything is kappa generated or whatever. All the categories are small, even though what I will say will be then technically wrong, because I will say R modules whenever. Okay, I don't care about size issues. Possibly R algebras, but mostly with R. Okay, so objects are modules and morphisms are module morphisms. And then we'll take C to be any category with finite products. Of course, it's not very difficult to see where I'm going with this. I want to define a sort of product on a category. And what I'm saying is that there is already a notion of products, like a direct product of objects. So that would probably obviously be some sort of product. Okay, so basically any category any reasonable category that you can think of, like category of sets, category, some sort of category of modules, rings, groups, monoids, whatever, varieties, topological spaces. It's very strong. Okay, so those are going to be my three source of examples. So now we're going to put some structure on our category to turn it into a monoidal category. So a monoidal structure on C, on some category C, is the data of so of course we need some way to multiply objects. So we're going to have, like if you have a set and you want to define a monoid structure on it, you have a product map. Here you also have a product map, but of course it's a functor because it's a categories. So it's a functor. So concretely, you take two objects and you output some sort of product object, and you can denote it with this tensor product symbol, which of course suggests what is going to be the product on the category. But this is the general symbol that we use. And since it's a functor, you not only need to multiply objects, but you also need to multiply morphisms. So if I have two morphisms, I can multiply them to get something from it. Okay, and of course this is functorial, so is compatible with composition, with the identity, everything. Okay. So I can multiply objects, and I can also multiply morphisms, which is already, of course, something which is different from just monoids. The category would have 2 layers. And of course, if you want a monoid, we don't just need a multiplication, we need a unit. So we are also going to choose some unit object. Which, so my general symbol will be I, or IC if I need to specify what is the ground category. Okay. Okay. I mean, so I'll comment on that later, but in a monoid, you don't need to add the units in the data because if there is a unit, then it's unique. But here, we do need to add it as data. Okay. So let's look at what that looks like on our examples. Okay. So let's take a discrete category. So what is, we're going to look at something like this to apply our definition.
Can I ask you something? So the this unit object,
yeah.
X tensor, the unit you asked it to be isomorphic to X or to be X?
I have for now this is not a definition because I have given no condition.
Okay.
Like the yes. Definition is not complete.
Okay.
The definition is not complete. So I'm just taking a look just precisely because there are several conditions that you can put, weaker or stronger conditions. So let's look at what that looks like. So yeah, what is a functor like this? Well, those are rigid categories. Those are discrete categories. Sorry, so discrete categories. So they are just sets. A functor between 2 discrete categories, if you think about it, what does a functor do? It takes object to object, so it's a function on the object level, and then it takes morphisms to morphisms. But there are no morphisms; they're just the identity. And the identity must be taken to the identity. So a functor between discrete categories is just a function. Okay? Discrete categories are just sets, and functors between them are just functions. So this is just a function. This is just a function from x times x to x. And a unit object is just an element. So from now on a discrete category, this just looks just like taking some sort of multiplication function and some distinguished element in x. Okay, so you see that I have not yet written what the conditions on all of this are, but you see that where we're going with this is just going to be a monoid structure on the set X, right? We're just asking for multiplication and distinguished objects. On the category of R modules, the orange one, what we're going to use is the tensor product as the notation, as the general notation suggests. So we have modules, so we have a tensor product of modules. Okay. And our unit object, of course, in the back of our mind, we know that the unit object should be like a neutral element for multiplication in some sense. And so what is a neutral element for multiplication with tensor products is just R itself, right? Seen as a module. That's going to be our example that we want to think of as a model example. And well, when C has finite products, when, of course, I would say it's kind of obvious what we're going to do. In general, in this general situation, we just take that the tensor product is the product, is the direct product of the 2 objects. Okay, and so what should be the unit object? So think about it. If we take the category of sets, for instance, you have a direct product of sets. What is a set? Such that if you take the direct product with it, it doesn't change anything. It's a set with one element, right? And generally speaking, what you want to do is to take a terminal element.
Is it the same as a final object?
I'm sorry?
Same as a final object?
Yeah, final object. Yeah, terminal final object, which exists because we have finite products, and the final terminal object is an empty product. So it's a product of length 0. And if you are not convinced by this trick, you say add it to the definition. Okay, so we have our examples. And so now we can try to look at what our actions should be. So clearly, we want our product to be associative because we want a monoid. A monoid is associative. Now, what should it mean? Okay. Also want the unit to be the neutral element. What I mean to be associative. If you look at this, for instance, about this concrete example, it is not true. So it is untrue that M tensor N. So sometimes I'm not going to put R in the tensors, just it is not equal to M tensor. This is untrue. Likewise with sets, it is not true that A times B times C is equal to A times B times C. They're not equal. They're not the same set. But no one cares. Right? No one puts parentheses on products of sets. No one writes, oh no, I've written R3, but is it R times R times R or R times? No one cares, right? Because those products are associative. But what does it mean? It's not associative. So it's associative up to a canonical isomorphism, right? And so that's exactly what we're going to put as structure as associativity. And likewise, it is also not true that M tensor R is equal to M, but it's canonically isomorphic to it. Okay, that's going to be. In case, on the other hand, in the discrete category, then it is equal. Because if you are isomorphic, you are equal in a discrete category. So in a discrete category case, we are going to have equality because there's just equality. There's no isomorphism other than equality. And that's what we're going to call a strictly monoidal category. I'm actually not going to write the definition because it's really not important. They are very rare. Like, it's usually not interesting to ask for equality. It just happens that in this discrete case, well, that's everything. That's what we have. So. But it can happen. It's not just discrete categories that can be strictly monoidal. Other cases exist. Also, natural cases exist. For instance, when the tensor product is given by composition of something, then the composition is actually associative. So what we want to do instead, as I finish the definition here, we want to add the data of some isomorphisms for every triple of object X, Y, Z. You want something like this, and you also want something that tells you that your unit object is neutral on the left. And that's also neutral on the right. Okay, so lambda for left, rho for right. And alpha because it's the first checker. No, for associativity. Okay. Of course, you want this to be natural in each variable. You want that if you have some morphism between some x and some x prime, the diagrams that you write are commutative. I'm not going to write every condition, but they should be natural in each letter. And they also have to satisfy some sort of coherence axioms that tell you that, okay, now suppose that, so now I can switch parentheses. If you work with a monoid, you say, oh, the product is associative. That means that I can parenthesize however I want. I can remove the parentheses because however I parenthesize is the same object, it's equal. In a category, what this proves is that however you parenthesize, you can apply this thing as many times as necessary, and the two parenthesizing will be isomorphic. But now we have to think, oh, isomorphic is maybe not good enough because I have several ways of unfolding the parentheses and applying my alphas to reparenthesize. And maybe those several ways give me different isomorphisms. So if I want to identify the two objects, I should need to know, oh, in which order did I reverse the parentheses? And that's annoying. That would mean that is what you're doing is not very well defined. You would have to worry about what you're doing. So we add those axioms, which tell you that you can apply those morphisms in whichever order you want. It's the same thing. So you can really remove, and actually it can be axiomatized in like 2 or 3 diagrams. I just don't want to write. But it's it means you can really remove the parentheses, and you can really simplify all the multiplication with I, and no one can tell you, oh, but what did you use to do this? There's only one way of removing parentheses. There's only one way of simplifying the unit elements.
Can you give like one example, or is it too complicated?
Oh, I mean, what is the isomorphism between
one of those rules, basically?
Yes, I can give one example. So for instance, you can say, oh, let's say I have something like this. What I can do is I can simplify the I here. But first, what I can do is say, oh, I use associativity to say that this is this, and then I simplify using this. So here I use rho of x, and here I use here I use in addition, here I use rho of x, and here I use lambda of y. But I want it to be the same, okay? Or you can have something with 4 objects which are parenthesized differently, and you want to first switch and then switch in other order. Okay? So this is a monoidal category. Okay? So in the case of a discrete category, it's just a monoid. Okay? This is just an equality. This is an equality. This is an equality. So it gives you that you have associativity and left unit, right unit. It's a monoid. But in general, you have something which is a little bit more solid. Okay, now I want to. Okay, so, I'm going to start completing my table here. So our first thing is monoidal, and now I want to keep track of what is a structure and what is a property. So, as we have seen, for a category, being monoidal is a structure, which is not surprising. Already being a monoid is a structure. If you have a set, something into a monoid is a structure. Not surprising. Now I want to wonder what is commutativity. What does it mean for a monoidal category to be commutative? Like I wonder, like, what is a commutative monoid? I know what it is, but what is a commutative monoidal category?
So when you say structure, it means basically data plus conditions, whereas property.
Yeah, it means that you cannot, if you ask me the question, is this category monoidal? I cannot answer yes or no. You're going to have to tell me more. Is it monoidal for what structure? Whereas if you ask me, I mean, just, okay, I understand. So for this one, it's not very surprising because already a monoid like if you ask me, is this set a monoid? I don't know. It's like for what multiplication, you know? But you can also already see a little bit of difference in the sense that for sets and monoids, having a unit is a property, and here the unit is given as data. So it's, yeah.
Is the unit unique up to isomorphism, or you need more data coming with the unit?
So the unit is unique up to isomorphism. So what? Let's do the usual proof.
Yeah.
Why in a monoid you have two units? It's unique. You take unit E prime. E times E prime is E because E prime is a unit, but it's E prime because E is a unit. Here do the same, but with the isomorphisms. I times J is isomorphic to I because I can simplify J because J is a unit on the right, and I can simplify, and that gives me an isomorphism between the two. Okay, so in this sense, the unit is really specified by the structure, but only up to iso. Okay, so what is commutativity? Of course, the naive first attempt is this, right? Commutative. And this is a definition that we can take. Unfortunately, it does not take a lot of convincing to see that it's not going to apply very much. As a general rule, asking for equality is always a bad idea. And asking for equality of objects is always a bad idea. Equality of morphisms is fine, but equality of objects is a bad idea. And of course, you see that in all examples, for instance, we want very much tensor products to be commutative, right? But it's not true, right? It's just isomorphic. And so obviously, we are going to have to weaken our condition to just having an isomorphism here. So, and of course, now I say, but being isomorphic is a property, but really what you want is not just say, oh, they are isomorphic. What you want to say, there is an isomorphism that I can actually use, which is the switch isomorphism. So what we want is some sort of data for each x and y. We want such an isomorphism, which is natural in x and y, and which might satisfy some axioms, again, of coherence, which tell you that if you apply it differently, it doesn't matter. Okay, so for instance, I can give one axiom that it should satisfy. So if you start with x times y times z, what you can do is first you say, I apply associativity, and then I switch these two blocks, and then I can apply associativity again. Or what you can do is first you switch inside the left parenthesis, then you apply associativity, and then you switch inside the second parenthesis. So each time you're applying one step, and there's no reason why those two things should be the same. So we add it as an axiom, and okay, and a couple of those. Okay, this is some sort of coherence axiom. Okay, just to see what it should look like. And so this is the definition of a braided category. Braided monoidal category. So it's sort of like a higher version of commutativity, but commutative up to some isomorphism, which satisfies good conditions.
I'm sorry, is braid not usually used to not require the invertibility, so that you just have
No, it's the weakening is that we will see braided compared to symmetric means that if you do it twice, it does not come back to the original.
Oh. And you also need to say that gamma is a natural transformation.
Yeah, it's natural in XMY. Yeah, everything is natural in XMY. Yeah. Okay, and so the thing is that we can see that our examples are a bit better than that. You can say that I can switch, and the question is, what happens if I switch twice? Well, obviously, I can do it. I can switch twice. Okay, here this is gamma xy, and here this is gamma yx. That gives me an isomorphism here, but doesn't have to be the identity. So the thing is, should we exclude things where this doesn't happen? We're not going to exclude them, but we're going to create a stronger condition. So we're going to say that C so I'm going to lie a lot in the notation. Technically, a monoidal category is a data of C, the tensor product, I, the associators, the left uniters, the right uniters. It's too long. Okay, so I'm either going to write C, like we usually do, like let V be a vector space. Of course, a vector space is not just a set, right? But I'm never going to write the associators and the uniters, just too annoying. And I'm also never going to write the gamma. Okay, that's right. We say that it is symmetric if this is the identity. If I switch twice, I did nothing. So most categories which are braided in nature, like in actual mathematical nature, most categories that are braided are symmetric, but there are interesting examples of things that are just braided but not symmetric. And I also keep it for some conceptual clarity later. So I'm going to add two new things, braided and symmetric. So we saw that if I take a category, being monoidal is a structure. Being braided is also a structure. But being symmetric is now a property. If you give me a braided monoidal category, I can answer yes, no to is it symmetric. Okay. Of course, our examples with modules or algebras and with direct products are symmetric. Okay. If you look at the isomorphism, how is the category of R modules, for instance, how is it braided? Well, I already forgot what was my color code for this middle category. Orange. Wait, what is it? What is the braiding? We call it the braiding. Of course, is defined by this, right? So if I do it twice, the identity, right? Likewise with direct product. If you think about direct product of sets, what is the canonical isomorphism between A times B and B times A if I switch the two objects. So if I switch twice, of course, it's the identity. Right? So our categories are symmetric. And for the discrete case, if it's braided, as we saw, braiding must be equality of y times x is x times y. So it means it's a cumulative monoid. So there's no, I mean, it's automatic. If it's braided, it's symmetric, right? Because it's so rigid. Nothing else can happen. Okay. We have our cumulative condition. Okay, so we know what, and we have two levels of cumulativity. We can be a little bit cumulative or very cumulative. Now, what are the functors? We know what a monoid is with category. What is a monoid morphism? So our first definition that we can write is that a monoidal functor, so a functor between monoidal categories, could be some sort of functor like this, such that so it's a morphism, right? It sends product to product, and it sends identity to identity. I mean, unit to unit, I should say. Of course, it's not the correct definition because I asked for equality, and you should not ask for equality. So this is a strictly monoidal functor, which in practice is not, I mean, unless for discrete cases, it's pretty not something that you want. Of course, what you're going to do instead is ask for isomorphisms with some compatibilities with associativity and with units. Okay. So you have to give for every x and y something like this, and something like this. Okay. This is what we call a strong monoidal functor, which suggests that there is something which is not strong.
Strong is less than strict.
Strong is less than strict. Yeah, strict is as strong as you can get. Strong is pretty strong. And there's, I mean, it's not called weak, but difficult weak.
We don't have to give the isomorphisms. We just have to.
No. It's data.
Okay.
It's data. Yeah, okay, but that's why I do not write this as a relation, but as an arrow.
Yeah.
You have to give an arrow. So, excellent question, because this tells us that being monoidal is a structure, which is already different from the case of monoids. If you have a function between two monoids, you can ask, is it a monoid morphism? Yes, no. There's equality or there's no equality. Here it's a structure.
Do you need any conditions like axioms on the isomorphism?
Yes, they should be compatible with associativity, with the associators. So like if you have some product like and you want to reduce to this, you have two ways of doing it. You can either first group these two and then include z, or you can do this two and then include z, you can include x, and you have to check if it's the same. Right, that's an axiom. And also for units, you have to see that this is compatible with tensoring with the units. Okay, I'm not going to write all the axioms, but the natural ones that you can think. Okay, so can we have one example of a monoidal function? Yes. Okay. It is true. With what structure?
Equality.
Yeah, the identity is actually is strictly monoidal. Well, it's not super interesting, but It's true. It's a fact. So one example I want to focus on is the following one. So let's C be monoidal, and let's take some object. Now I can define a monoidal functor from the discrete category of n. See? I can do this. So this is a monoidal category because n is a monoid. Recall that a discrete category being monoidal just means that this is a monoid. So of course I'm using the canonical structure of monoid addition, in a trap. And C is just any monoidal category. And I can define this. And this, I claim that there is a natural canonical monoidal structure on this functor. What is this saying? I want f of n so of course this means x tensor x tensor x tensor x n times, and I don't need to specify the parentheses because we don't need parentheses. So technically, I hear you, Karen. This is not well defined. This is not a well-defined addition, but it doesn't matter. You can choose your favorite way to associate things, on the left, on the right, using fantasy stuff. And of course, there's only one nonsensical way to do this. It's to use the associators, right? It's to I associate things. Okay, so there's a natural monoidal structure on it. And now for me, that's improving. This thing is very important. Because if you think about monoids, you know that if I have a monoid, for every object, defining a monoid morphism from n to a monoid is the same thing as picking an object. Because I send 1 to something, and then you take you don't have any choice, right? It's more commonly known for groups, like a morphism from Z to a group is the same thing as picking just an object. Otherwise saying n represents the forgetful functor from monoids to sets, okay? Or n is the free monoid in one object. This is the free monoidal category in one object. Okay? So choosing a monoidal morphism like this is just picking the element x. This is completely canonical. And we'll see later that if we switch n a bit, it will be a little bit more simple. And this is naturally a strong monoidal. Okay, so that gives us a very natural notion of monoid morphisms between monoidal categories. But sometimes we want something a little bit less strong, as the name suggested, because sometimes you have something like, if I give myself two objects, one, and if I give myself coming from x and coming from xy, I can construct something coming from x times y. But sometimes this won't be an isomorphism. Let me give you an example. So I'm going to use as an example, or rather for now a counterexample, I guess, a functor from the category of rings to the category of categories to a ring R. I associate its category of modules. For any ring, I have a category of R modules. And it's almost monoidal in the sense that I should have also I should of course I should specify what is the modular structure I put on this. So here I put the tensor product of rings, and here I put the direct product of categories. So a monoidal structure on this functor would be something like this. And of course, what we want is to say, okay, what is this? What is the natural functor? If I have an R module and an S module, how do I construct some R times S module? Well, of course, I do this. If M is an R module and M is an S module, it's an R times S module. So it works, but it's not an isomorphism, right? Not every R times S module is useful. Just doesn't work. So I just have a morphism.
It could not work, that's resolved it.
Yeah, I can solve. Or I can fix some ground ring and say I work with K algebras. No. Okay, so and this kind of things happens very often. I have one thing from here, one thing from here. I can combine them to get something like this, but it's not an isomorphism. Okay, well that leads us to say let's weaken our condition a little bit. And we say that a lax monoidal functor is like this. I only have morphisms. And that's why I wrote it in this direction. Maybe when you write morphisms between monoids, it's more usually what f of x times 1 is equal to f of x times f of y. You write it in this direction. But it turns out that with all this business of monoidal categories, it's in this direction that it makes the most sense. The other direction also exists. It's called an up-lax monoidal functor. But okay, in nature and in particular in what I do, is this direction is, of course, the fact that the terminology is in this direction shows that that's sort of, this happens more often. Okay, so I have a weaker condition.
Okay.
Yeah.
Can I got confused. So what is the monoidal structure of cat?
The direct product.
Just the product.
The product, yeah. Cat is one example in the third column of category with finite products.
So this you are saying then, so now 2R modules, the direct product is the same as the...
No.
Oh, sorry.
The functor sends a ring to the category of R modules.
Ah, okay, sorry. Yeah. And one level below.
Yeah. Okay, so we have strong and lax monoidal functors. So technically here, so being monoidal functor, being a lax monoidal functor is a structure, and then being strong among the lax things is the property that these are actually isomorphic. So it is a structure, but if you distinguish between lax and strong, then the additional thing of being strong is then a property. I'm not going to. Okay, so we have our morphisms between monoidal categories. We have our monoid morphisms, and now we can compose them. And it's easy to see that there is a natural, that if you compose two monoidal functors, there's a natural structure of monoidal functors. So, of course, we have to specify the structure, right? It's not a property. You cannot say, oh, the composition of two monoidal functors is monoidal. You have to say there is a natural monoidal structure on it. Okay? It's the obvious one that you can think of. It's like, I have this. Now let's assume I apply some G over it. Well, first step is, okay, so if I have this. Of course, first I apply the property for F. That gives me a morphism that goes like this. And then I apply the property for G, which gives me the feedback like this. It's more structure. Okay, and now we have remember another layer is that we have natural transformations. So what is a morphism between two monoidal functors? What is a monoidal natural transformation between two monoidal functors? One here. So you have two functors like this between monoidal categories, and you have some natural transformation. Yes. And you say it is a monoidal natural transformation if you have these diagrams. So this says that the behavior with the units is natural, is the one you expect. So F is monoidal, so we have something like this. G is monoidal, so we have something like this. Phi goes from F to G, so we have something like this. This should commute. And if you have F is monoidal, so you have this. G is monoidal, so you have this. This is the tensor product of phi this is phi for the object X times phi for the object Y, and this is phi for the object X times Y, which should also commute. Okay, so this should be compatible with it. Yeah.
With the first diagram, I don't really understand it, because what should commute? Because how can you get a morphism from ID to f of I?
That's one of the morphisms, but I raised it, but that's one of the two conditions to be a monoidal functor. Basically,
okay.
a monoidal functor sends unit to unit.
I was confused with the C and D, I think, but I see now.
Oh, yeah.
Okay.
Yeah. It's no, it's okay.
It's probably correct.
It's fine.
I was confused. Yeah.
But now you see that being a monoidal transformation is a property. Okay? Being like, if you have a natural transformation between two monoidal functors, you can ask whether or not it is a monoidal natural transformation. It's not a structure, it's a property. So actually, I do not have as much time as I should have wished. So going to be a bit quicker with the commutative stuff, with the symmetries. Okay. So suppose that now that C and D are braided. Okay. You have some monoidal functor. You want to see, is it compatible with the switch morphism? Okay. So you write the diagram which says that if I switch first inside the functor and then I apply on, if I switch after I apply the monoidal property, is it the same thing? That tells you that being a braided monoidal functor is a property now. Okay? Is you do not have to add any structure on it. Is you have a switch morphism, are you compatible with it? And now say that we are not braided, but symmetric. What more do you ask? Nothing. There's nothing more to ask. You're already compatible with all the structure. Being compatible with a property is nothing. You can be compatible with structure. Being compatible with property doesn't exist. So this is nothing. Okay? And it will be the same. Once you have this natural transformation between two monoidal functors, it's a property that it's monoidal. But now let's say that those two functors are braided monoidal. what more can you ask of the natural transformation? Well, nothing. They satisfy some additional property. There's nothing left to be compatible with. And even more things. Okay? So you have some sort of table like this, and we could, I mean, if we work in higher category context, we could extend in both directions, and we would have this sort of triangle. Okay? So the reason for this is that, so you know that a monoid is like a category with one object, right? That's something like that you do when you learn categories. If you have a category with only one object, but it's one object with a bunch of endomorphisms, and they compose, that gives a monoid. Now, a monoidal category is a two category with one object. And now a braided monoidal category is a three category with one object and one morphism. And just the two morphisms are left. And a symmetric monoidal category is a four category. Do I need to go to four? Yeah, four category with one object and one morphism and one. And you can do things like that. And you can ask, okay, but what happens if I go one step further? Let's take a five category with one object, one morphism, one two morphism, and one three morphism. But it's diagonalized. You cannot be more commutative than being symmetric. On the other hand, if you have a two category, you can say, oh, a two category, let's take a three category with one object. Then there's still two stairs left. That's just a monoidal two category. Let's take a three category, or let's take a four category with one object and one morphism. That's a two category, which is monoidal, but a bit more commutative. But then you will have more steps in commutativity. You see that when you go from sets to categories, we had a second step of being commutative. It can be a little bit or very commutative. But each time with two categories, there are three steps. You can be braided, you can be symmetric, but there's something in between. Okay? So you can have like a whole bunch of layers of commutativity in higher category. Okay? But we don't go into just mentioning it because I think it's interesting to see where this distinction comes from here. Okay. And now I have just a couple minutes left to talk about braided objects. I will do the connection with braided objects. So, we're going to look at the following example. What is let's take some monoid M. What is a monoidal functor from M to the category of R modules? So first, what is a functor? This is a discrete category. So functor is just saying, well, for each object here, I pick an object. There's nothing more because there's no morphisms here. So just a functor I'm just choosing some R module. I'm just choosing some R module for each M. And I can order them if I want to into the object. Okay. If I want, I can take the direct sum. That's my choice. I can do that. And that's a graded R module. It's graded over M. Okay, we have a component for each M. There's nothing more. Like there's nothing more. Now, what happens if this functor is monoidal, lax monoidal? Well, I'm saying that I need to have some sort of R linear map here. And this is if you have, and also morphism like this. And this is exactly the structure of a graded algebra. It's like if we define what is a graded ring or graded algebra, this is exactly it. You have to multiply a homogeneous element of degree m and a homogeneous element of degree n, and it gives you something that will be m plus n, and it's enough to do it on the homogeneous part because then you can extend it uniquely by combination. And so my argument is that this is the correct definition of a graded module, and this is the correct definition of a graded algebra. Because when you do graded algebra, you quickly realize that you really do not care about the ring properties of this ring. You only care about the homogeneous elements. For instance, you don't work with ideals. You work with homogeneous ideals, which are only defined by the homogeneous part. And you want it to be, if you want it to be a graded field, you only want the non-zero homogeneous element to be invertible. And if you want it to be graded, a graded domain, you only want the product of two non-zero homogeneous elements to be non-zero. And actually, everything is formulated using this and not using this direct sum, which is just here to, bundle everything into a single object. But this does not matter. This is a graded ring, and this is some ring which can be realized from this actually graded ring. But that's my point of view on graded objects, that they are fundamentally lax monoidal morphisms from discrete monoidal categories to your category of interest. And then it turns out that it's easy to check that exactly a monoidal functor, a monoidal natural transformation between functors is exactly a graded morphism, graded ring morphism if you're a graded ring, and everything. So the category of graded algebras is equivalent to the category of monoidal functors like this. Okay, and so you say, okay, sure. Like we took a perfectly simple object and made it more complicated. Is that good? I think it is, because then that gives you a recipe to create graded rings. Okay, because now, okay, I'm going to conclude with this. So say you start with some category, some monoidal category C, and you happen to have some monoidal functor like this. Okay. So I didn't have a lot of time to talk about it. It's fine. Then, if composing with F gives you I'm going to say, okay, I'm going to. This is the category of lax monoidal functors, which is just the category of M-graded algebras, by what I just said, right? This is just an M-graded algebra. So this is just composing with F. So if I have a monoid morphism, if I have a monoidal morphism like this, I compose it with F, and it goes to this. That gives me a graded algebra. And this is a general recipe that you can do. And a good example that I used is to take K-theory. So if C is a category of algebra, you can use a functor which gives you a K-theory, let's say a building group, okay, so Z module. And K-theory is monoidal, okay? Basically, K0 of A times K0 of B goes to K0 of A tends to B, saying that if I have a projective module on A and a class of projective modules on A and a class of projective module on B, I have a class of projective modules on N tends to B. Or if we do more geometric, if I have a vector model or something and a vector model or something, I can take the tensor product to get a vector model. So you can do this with K-theory. And the thing is, okay, but now what about this? Well, I already told you how to do it when the monoid is N. I said that this was automatic. For any single object, you automatically get such a thing, right? But it's the stupid one. That would give you the graded thing, which is just this. So that's, it exists canonically. You don't have to make any effort to do it, but it's not super interesting. But now what if I replace N with Z? If you're in a monoid, the monoid morphism from Z to your monoid, instead of taking any element, you have to take an invertible element, because you have to also have the image of -1. But for categories, it's more complicated than that. Taking a morphism from Z to C is saying, I have to send one to an invertible element, but I have to choose an inverse, and I have to choose an isomorphism between X and its inverse to the unit. So it's a choice not only of invertible element, but of inverse. And this category is the, if you press by Z, is the category of all possible choices of choosing an inverse. And now what happens with it when you replace it by Z mod N? Well, that gives you some sort of torsion. If you have here an abelian group, Z mod N to this abelian group is the group of N torsion elements. And here, so for this to make sense, you have to assume that C is at least graded and even symmetric, otherwise it won't work well. But this gives you like a category of all possible choices of N torsion of objects. And so I applied that to Z mod 2. And if you take not K-theory, but Hermitian K-theory of algebras with involutions, you also, here you have a category of algebras with involutions. Here you also have, let's say, abelian groups. And here you have Hermitian K-theory. It's also Lax monoidal. And that also gives you graded rings of K-theory. But for this to work, you need a bit more. You don't only need the object to be invertible or to have torsion. You also need it to, yes, but I started 10 minutes late almost because of the break. You also need to have this extra condition that the switch, if you take not X and Y but S and X, you have the switch here, and you need it to be the identity. Because it's the case here. Here, the switch is the identity. So if you want to have something which is strong monoidal and symmetric, you need here also the identity. And you can say, but does it happen? And with this context of K-theory, yes, it does, when the algebra is an Azumaya algebra. And so that's why you can construct graded K-theory rings for Azumaya algebras with the general set. Thank you.